Welcome to chemistry class. Students, can you tell me the composition of pure air? Composition of pure air. Do you know that? Okay. Let me answer this. In air, the percentage of oxygen by volume is 21. Percentage by volume of nitrogen is 78. 78 plus 21, it is 99. So 99% by volume is oxygen and hydrogen. I mean, in 100 ml of air, there is 21 ml of oxygen and 78 ml of nitrogen. What about 1 ml? 1 ml, what is that? 1 ml, I mean 1% by volume is noble gases. I repeat, in pure air, the percentage by volume of noble gases is 1%. That is, if we are taking 100 ml of air, there will be 1 ml of noble gases. So, students, today's discussion is about noble gases. Noble gases? Can you call them inert gases also? You know, these are also called inert gases. And what are these gases? How many elements are present? And it belongs to which group in the predictable? These elements or these gases were also called zero group elements. Right now, group 18 elements. The first, let's see why these elements are called noble gases or inert gases. Now, question comes, which one is correct? Inert gases? Should we call them inert gases or noble gases? Which one is correct to say? You see, before 1962, these gases were called inert gases. Okay? And after 1962 onwards, these gases, they are nowadays called as noble gases. Why this is so? Just see the electronic configuration. All these elements have got 8 electrons in the outermost shell except helium. They have got 8 electrons, Ns to Np6. So, they have quite stable electronic configurations. Because of the stable electronic configuration, these elements have the little tendency to enter into chemical combination. They don't enter into chemical combination, neither they lose electron nor they accept electron. They are also not interested to share the electrons. So, they don't enter into chemical combinations. That means they are chemically inert. They don't have any tendency to react to the other elements available in the predictable. That is why these elements were called inert gases. But in the year 1962, scientist Neil Bartlett tried to prepare a compound by reacting oxygen with platinum hexafluoride. He got a red colored compound, that is O2PTF6. By reacting oxygen with platinum hexafluoride, he got a compound, colored compound, that is O2PTF6. So, O2, what he found? O2 has the same ionization energy as that of xenon. This prompted him to prepare a compound with xenon, because he thought if oxygen can form a compound with platinum hexafluoride, why not xenon? Because xenon also has the same ionization potential, almost same ionization potential as that of oxygen. So, xenon can also form a compound with PTF6. So, he tried to prepare a compound by reacting xenon with PTF6, and he got the colored compound XPTF6. This was the first noble gas compound prepared in the laboratory. Okay. Since then, many compounds of xenon have been discovered, particularly with electronegative elements like oxygen and fluorine. Xenon and krypton usually they form compounds. Krypton, only one compound of krypton is available, but xenon forms a large number of compounds with electronegative element such as oxygen and fluorine. Okay. So, that is why right now these elements are called noble gases, no more inert gases. So, it is correct to say noble gases. Now, question comes, why these elements are called zero group elements? Because since they have 8 electrons at the outermost shell except helium, they have the little tendency to enter into chemical combination. I have already discussed that. So, their valence is 0, their valence was supposed to be 0. That is why They are called zero group elements in Mendeleev periodic table. Okay? But in the modern or long form of the periodic table, these elements are group 18 elements, 18th group elements, noble gases. Correct to say noble gases, not inert gases. Okay? So, we will discuss the physical and chemical properties as well as the compounds of the noble gases. First, we will discuss the physical properties of noble gases. Before discussing the physical properties, let us see the noble gases availability and occurrence. All the noble gases except radon. You know noble gases, how many noble gases we have? There is 6 elements in the 18th group: helium, neon, argon, krypton, xenon and radon. I repeat, helium, neon, argon, krypton, xenon and radon. Radon is radioactive, not available in air. Otherwise, all the noble gases are available in air and composition is 1% by volume in air. All the noble gases except radon occur in the atmosphere. I have discussed this one, and the percentage by volume is 1%. Helium and sometimes neon are found in minerals of radioactive origin, such as pitchblende, the clevite, monazite, etc. The commercial source of helium is natural gas. In natural gas, the helium is available to a greater extent. Xenon and radon are the rarest element of the group. Radon is often as a decay product of radium. Radon is radioactive. So, after the alpha emission, the radium gives the radon. The reaction displayed on a TV screen. This is the occurrence of the noble gases. Coming to physical properties. First physical property we will discuss the electronic configuration. I have discussed the electronic configuration. If you find the electronic configuration of noble gases, there are 8 electrons in the outermost shell except helium. Helium has got 2 electrons. All other noble gases have octet configuration. 8 electrons in the outermost shell. Coming to ionization enthalpy. What about the ionization enthalpy? Noble gases very high in the predictable. Why this is so? Because of stable electronic configuration. They have got 8 electrons in the outermost shell. They are quite stable. 8 electrons, highly stable. Much more energy is required to remove the electron from the outermost shell. That is why they have very, very high ionization enthalpy, these elements. And what about the trend of the ionization enthalpy? As usual, down the group, ionization enthalpy decreases. Down the group, ionization enthalpy decreases because atomic radius increases. So, this is the electronic configuration and ionization energy. You know, helium is the element with the highest ionization enthalpy in the predictable. All the noble gases have very high ionization enthalpy or ionization energy. About the atomic radius, increases down the group. As usual, number of cells increases, so atomic radius increases down the group. It is obvious. We have discussed so many points in p block elements about the atomic radius, usually increases down the group. Electron gain enthalpy. What about the electron gain enthalpy? What is electron gain enthalpy? Tendency to accept electron so that heat can be evolved, energy can be released. Okay. Can you expect that noble gases will accept electron? Why they will accept electrons? They have got 8 electrons in the outermost shell. They have got 8 electrons. Why they will accept electrons? They don't have any tendency to accept electron. If after electron will be added, we have to supply energy. That means the electron affinity, they have negative electron affinity or positive electron gain enthalpy. That means energy must be supplied for addition of electron to the noble gases. So, they have positive electron gain enthalpy. Okay. Why this is so? Because of the stable electron configuration, they don't have any tendency to accept the electron. Is that clear? Then physical properties, all the noble gases are monoatomic. Monoatomic. Now question comes, why they are monoatomic? Why not diatomic? We found in chalcogens they are diatomic, like O2 is diatomic. In nitrogen family, nitrogen is diatomic, halogens are diatomic, but noble gases they are monoatomic, like we can write helium He, neon Ne, argon Ar. They are not, it is not He2. Why? Number 1, the bond order is 0. Bond order, number of covalent bonds present between 2 atoms. Bond order we can calculate from the molecular orbital theory, according to which bond order is equal to number of bonding electron minus antibonding electron divided by 2. Bond order 0, noble gases, bond order 0, that is their monoatomic. Okay. Also Poisson's ratio indicate that they are monoatomic. CP-CV ratio, it is 1.66 for noble gases, so they are monoatomic. What about the color? Colorless. Solubility, sparingly soluble in water, but solubility increases down the groove. Now important question, students. The question can be asked that are in the noble gases in the increasing order of their solubility. The most soluble noble gas is, that is I mean xenon here. I am not talking about the radon because radon is radioactive. So, if we will consider the noble gases here, we will discuss mainly 5 noble gases: helium, neon, argon, krypton and xenon. Xenon is more highly soluble. Why? It can be easily polarized. The solubility increases down the groove, but they are sparingly soluble in water. Most soluble, xenon. Okay. They have very low melting and boiling points. Yes, because they are monoatomic, and the force of attraction only exists between them is weak van der Waals force of attractions. That is why the melting point, boiling point very low. But what about the trend of the melting point and boiling points? Increases down the groove. Helium has the lowest boiling point, whereas xenon, it has very high boiling point. Why? Why boiling point, melting point increases down the groove? Can you answer, students? This concept we have discussed so many times. You can answer yes. So, helium has the lowest boiling point because of very weak intermolecular force of attractions. As the size increases, van der Waals force of attraction increases, the melting point, boiling point increases, the melting point, boiling point increases down the groove. Coming to chemical properties, noble gases are least reactive elements, and their inertness is obviously due to the stable electronic configurations, that is 8 electrons in the outermost shell except helium. So, they are least reactive, they do not enter into chemical combination usually. Ionization energy too high, so they cannot lose electrons. Positive electron gain enthalpy, so they do not have any tendency to accept electron to form anion, neither they can form cation nor they can form anion, and they also do not have any tendency to share electrons. So, they are least reactive elements, and the first noble gas compound, discovery of the first noble gas compound, I have already explained that. Coming to radon compounds, compounds of radon have not been isolated, but only identified by radioactive technique, and no true compounds of argon, neon or helium are yet known. So, I have already told you the noble gas compound mean compounds of xenon and krypton because of the low ionization energy. Though radon can form compounds, but it has not yet been isolated. And argon, what about the helium, neon and argon? Do not form any compounds. So, the compounds of noble gases mean compounds of xenon, okay, usually compounds of xenon, and particularly with electronegative elements such as oxygen and fluorine. Okay. And what about the krypton compounds? Only one compound of krypton have been isolated, that is studied in detail, that is krypton difluoride, KrF2. Okay. These are the compounds of noble gases. Then coming to compounds of xenon, xenon forms a large number of compounds with fluorine and oxygen. About the fluorine, xenon fluorine compounds, xenon form the compounds binary fluorides XeF2, XeF4 and XeF6 by direct reaction of elements under appropriate experimental conditions. Okay, what are the experimental conditions displayed on a TV screen? The direct combination here. So, how to prepare xenon difluoride? The xenon difluoride is prepared by reacting xenon with fluorine, where xenon is taken in excess at 673 Kelvin and under 1 bar pressure. How can you prepare XeF4? Another noble gas compound, it is xenon react with fluorine in the ratio. So, what the ratio here? 1:10 ratio. I mean 1 part of xenon with 10 or 1 volume of xenon with 20 volume of fluorine. Okay, in that ratio they react to form XeF4. And the third compound, that is XeF6, here it is also prepared by direct combination when xenon react with fluorine in the ratio 1:20. 1 part of xenon gas with 20 parts of fluorine, it gives XeF6. These compounds XeF2, XeF4 and XeF6 that prepared by direct combination under appropriate condition, I mean at different temperature and pressure. Well, students, We have already discussed about the preparation of xenon fluorine compounds. Let me once again refresh you this. Xenon react with fluorine to form XCF2, XCF4 and XCF6 at different temperature and pressure. If we prepare XCF2, we have to take excess of fluorine. Xenon react with excess of fluorine to form XCF2 at the temperature 673 Kelvin, I mean 400 centigrade and 1 bar pressure. XCF4 is prepared by reacting xenon with fluorine in the ratio 1:10 at the temperature 873 Kelvin, I mean 600 centigrade and under 7 bar pressure. The XCF4 is prepared. XCF6, it is prepared by reacting xenon with excess of fluorine in the ratio 1:20. I mean 1 volume of xenon react with 20 volume of fluorine at the temperature 873 Kelvin at high pressure 60 to 70 bar pressure to form XCF6. So these three compounds are prepared by direct combination of xenon and fluorine. Then XCF6 is also prepared by reacting XCF4 with dioxygen difluoride. So dioxygen difluoride, when react with XCF6, it gives XCF6 at 143 Kelvin. The reaction displayed on your TV screen, XCF4 plus O2F2 gives XCF6. XCF2, XCF4, so xenon difluoride, xenon tetrafluoride and xenon hexafluoride all are colorless crystalline solids and they sublime readily at room temperature. So they are colorless crystalline solids. All these fluorides, three fluorides of xenon, xenon difluoride, xenon tetrafluoride, xenon hexafluoride, all are colorless crystalline solids and sublime at room temperature. Powerful fluorinating agents. These fluorides are powerful fluorinating agents. That means they can provide fluorine to other elements. They can be readily hydrolyzed even by traces of water. Okay, for example, the reaction is displayed on a TV screen, that is xenon difluoride react with H2O to form xenon, HF and O2 gas, oxygen gas is liberated here. Okay. So can you tell me what type of reaction it is? Is it a redox reaction or any other reactions? It's a redox reaction here. Which one is the oxidizing agent? Obviously xenon difluoride. Why? Now the oxidation state +2 in xenon difluoride. See, let me write the reactions on the whiteboard. Let's have a look here. Xenon, HF and O2. Balance it. So 2 xenon, 4 HF. Okay. See, what the oxidation state of xenon here? +2. It is 0, +2 to 0. So it is reduced. Hence, XCF2 is an oxidizing agent. So oxidizes whom? It oxidizes water. It oxidizes water to oxygen. So this is a redox reaction. This is one of the important reactions. Question can be asked to you that how xenon fluoride react with water. Xenon difluoride when react with water gives xenon and liberated oxygen gas. Remember, all these fluorides are colorless crystalline solids. They are good fluorinating agent, and how they are prepared. I have already discussed their preparation. All are prepared by direct combination of xenon and fluorine. Xenon combines with fluorine at different condition of temperature and pressure to give XCF2, XCF4 and XCF6. Students, you have to remember this. The question can be asked, a long question can be also be asked to it, that how can you prepare xenon fluorides. Then the next property or next compounds of xenon, that formation of addition compounds. Addition compounds, xenon fluoride reacts with fluoride ion. It reacts with fluoride ion. Fluoride ion acceptors to form cationic species and fluoride ion donors to form fluorinescence. See the reactions. XCF2 reacts with PF5 to give XCF5 plus and PF6 minus. So it forms an addition compound with phosphorus pentafluoride. Here XCF2 acts as a fluorinating agent. Okay, it is a fluoride. You see, XCF2 reacts with fluoride ion to form cationic species and fluoride ion donors to form fluorinescence here. So you see, XCF2 react with PF5. What it gives? It gives XCF2 plus PF5. It gives XCF plus and PF6 minus. So it gives an addition compound. So acts as a fluorinating agent. Similarly, XCF2 react with IF5 to form XCF5 plus and IF6 minus displayed on the TV screen. With antimony pentafluoride, same reactions, XCF5 plus and antimony hexafluoride ion. So with S block fluorides and alkali fluorides, it is F minus an acceptor. I mean XCF2 is F minus an acceptor. With other, it is F minus an donor. So here XCF2 is F minus donor with the reaction displayed on the TV screen. With PF5, F minus donor. With IF5, yes, with IF5, F minus donor. With antimony pentafluoride, F minus donor, etc. But see, with cesium fluoride, see the reactions that is displayed on your TV screen. Cesium fluoride, what is the compound form you see? Cesium fluoride. So with S block fluorides, it is F minus acceptor. You see the xenon hexafluoride here. With S block fluoride, what is the S block fluoride here? Cesium fluoride is the S block fluoride. So with cesium fluoride, XCF6 acts as F minus acceptor. But with PF5, XCF2 acts as F minus donor. Addition compound it forms. This is S block fluoride, cesium, alkali metal, S block elements. So this is S block fluoride with XCF6, S block fluoride with XCF6. Here XCF6 is F minus acceptor. It accepts F minus ion from cesium fluoride. But see, with PF5, XCF2 F minus donor. It donated F minus ion so that PF6 minus is formed. It was PF5, now it becomes PF6 minus. See, with cesium fluoride, XCF6 accept F minus ion. It was XCF6, now it becomes XCF7 minus. So this you have to remember. With S block fluoride, the xenon fluorides are F minus acceptor, and with other fluorides like iodine pentafluoride, that antimony pentafluoride, it is F minus donor. Okay. Then xenon oxygen compounds. Next compounds of xenon, it is xenon oxygen compounds. Xenon oxygen compounds, how they are prepared? Hydrolysis of xenon tetrafluoride and hexafluoride. Very important reaction, students. Many often this question has already been asked. This question has already been asked many often, that what happens when XCF4 and XCF6 hydrolyzed. XCF4 upon hydrolysis gives an explosive compound XCO3, xenon trioxide, and with XCF6 with water, it also gives the explosive xenon trioxides, XCO3. Partial hydrolysis of XCF6 gives fluorides, XCOF4 and XCO2F2. The partial hydrolysis is displayed on a TV screen. That is XCF6 with water gives XCOF4, XCF6 with water also gives XCO2F2. What about XCO3? I have already told you. XCO3 is a colorless explosive solid under its pyramidal molecular structure. XCOF4 is a colorless volatile liquid. XCO3 is a solid. XCOF4 is a liquid under its square pyramidal molecular structure. Let us see what are the structure of XCO3, XCO4, XCO2F2. Okay. So xenon oxygen compounds, these are prepared. Xenon oxygen compounds are prepared by hydrolysis of XCF4, XCF6, that is XCF4 and XCF6 upon hydrolysis gives XCO3, XCO3 and other compounds like XCOF4, XCO2F2. Where XCO3 is a colorless solid, XCOF4 prepare the is volatile liquid. Okay, these are xenon oxygen compounds prepared by complete hydrolysis and by partial hydrolysis of XeF4 and XeF6, xenon tetrafluoride and xenon hexafluoride. Let us see what are the structures of the fluorides and oxides of xenon, because we have already prepared XeF2, XeF4, XeF6, XeO3, XeO2F2, etc. Xenon fluorides we have prepared by direct reaction between xenon and fluorine. The oxides and oxygen fluorides, they have been prepared by partial hydrolysis of the xenon tetrafluorides and hexafluorides. So, first we will discuss the structure, I mean the shapes of xenon fluorides, then we will come to oxides, etc. So, first the structures and shapes of xenon fluoride. The first compound of xenon is XeF2. We will discuss its shape and the structure of XeF2. You tell me, what is the hybridization of xenon here? Can you tell me, students? You know hybridization? So, how many orbitals are involved in hybridization of xenon to form this compound XeF2? From XeF2 it is clear only 2 electrons of xenons they have used in the bond formation with fluorine. Why? Because fluorine can use only 1 electron for covalent bond formation. So, xenon uses 2 electrons for the 2 fluorines. But you know that xenon has got 8 electrons in the outermost shell. Out of the 8 electrons, 2 electrons are used in the covalent bond formation with fluorine. Now, 6 electrons left in xenon. So, these 6 electrons we can say 3 lone pairs. So, xenon has 3 lone pairs and 2 bond pairs. We can also calculate by using the formula. So, what the formula to calculate the hybridization? Students, you all the students know how to calculate the formula to predict the hybridization of central atom. So, let me once again refresh you the formula to calculate the to predict the hybridization of central atom. What the formula here? That steric number calculation. So, how to calculate steric number? That is total valential electron of molecule, total electrons available in the valence of all the elements in the molecular ion divided by 8. So, xenon has 8 electrons in the valence shell, fluorine has 2 electrons in the valence shell. So, all total number of electrons available in the valence shell of XeF2 is 22 divided by 8. That gives Q plus R by 2. What is R here? Remainder. What is Q? Number of bond pairs. Number of bond pairs. And what is R by 2? Number of lone pairs. Number of lone pairs. Okay. The number of lone pair plus bond pair gives the hybridization of central atom in a molecular ion. So, if the steric number is 2, hybridization is sp. If it is 3, steric number is 3, hybridization is sp2. If it is 4, sp3, 5, sp3d, 6, sp3d2, 7, sp3d3. I repeat, if the steric number is 2, it is sp. Steric number 3, sp2. Steric number 4, sp3. Steric number 5, sp3d. 6, sp3d2. 7, sp3d3. So, what is the steric number? Let us see here. In XeF2, what is the steric number? It is coming, it is 2 plus remainder 6 by 2. So, it is 2 bond pair Q plus R by 2, 2 bond pairs R by 2, number of lone pairs 3 lone pairs, all total 5. When steric number is 5, what is the hybridization of central atom in the molecular ion, students? Yes, it is sp3d. So, in XCF2, xenon is sp3d hybridized, and all the 5 sp3d hybrid orbitals are how they are arranged in space. It is trigonal bipyramidal geometry. I repeat, trigonal bipyramidal geometry for sp3d hybridization. But what is the shape of XCF2? It has got only 2 bond pairs. It's the bond pair which predict the shape of the molecule. From the hybridization, we got to know that arrangement of the orbital in space, that is trigonal bipyramidal. But what is the shape? Shape, it depends upon the number of bond pairs. How many bond pairs? 2 bond pairs only. So, how it is arranged? How to place the lone pairs and bond pairs? The lone pair must be placed in such a way so that repulsion between them is minimum. Otherwise, a repulsion is more, energy is more, unstable. So, how to place the lone pair? Lone pair must be placed at equatorial position and bond pair axially. Lone pair here, lone pair here, lone pair here, that is equatorial position. And the central, there is xenon, central atom xenon here. One bond pair, another bond pair. The shape is linear. Let me show you here on the whiteboard. Look at the whiteboard here. Here, the lone pairs occupy equatorial position. Xenon centrally placed. Bond pairs axial position. Then what is the shape of XCF2? Linear. Shape of XCF2 is linear. Students, is that clear now? So, if the shape of the XCF2 is asked to you, what is your answer? Hybridization sp3d. It has got 3 lone pairs, 2 bond pairs, hence steric number 5. Steric number 5, hybridization sp3d. Shape is linear because the 2 fluorine atoms occupy the axial positions. Remember, in trigonal bipyramidal geometry, the electronegative atoms occupy axial positions. Lone pair occupy equatorial positions. Is that clear? I repeat, in trigonal bipyramidal geometry, electronegative atom prefers to occupy axial positions and lone pair equatorial positions. So, shape is linear. Coming to next molecule, it is the XCF4, xenon tetrafluoride. Xenon tetrafluoride. Let us calculate the steric number here. You know the formula? So, the steric number of xenon in XCF4, xenon tetrafluoride. How to calculate steric number? Total number of electrons available in the valence shell of all the atoms. Xenon 8 electrons, fluorine 7 electrons. How many fluorines? 4 fluorines. All total how many electrons? 28 plus 8, 36 divided by 8. That gives Q plus R by 2. So, what is Q here? 4. What is R here? 4 by 2. This is, what is this? Yes, yes, it is bond pairs, correct. And what is this? Yes, it is lone pair. Bond pair plus lone pair, how many? 6. If steric number is 6, what is the hybridization? You know this? Yes, it is sp3d2. So, hybridization sp3d2. Then what is the geometry? I mean, how the orbitals are arranged in space. You know, sp3d2 hybrid in sp3d2 hybridization, there are 6 orbitals. How they are arranged in space? Octahedral arrangement. So, sp3d2 hybridization, arrangement of orbitals is octahedral. Shape is, I mean, geometry is octahedral. But what the shape of XCF4 molecule? How many bond pair it has? Bond pair 4. Lone pair 2. So, where to place the lone pair and where to place the bond pairs? So, here lone pair you can place anywhere, but and what is the shape of the sp3d2 hybridization? what the shape of the XeF4 molecule? XeF4 molecule is square planar. It is square planar. So shape is square planar. Hybridization sp3d2. Geometry is octahedral. Let me show you the shape of the XeF4, which is called square planar. This is square planar geometry of the XeF4. But arrangement of the orbital in space, octahedral arrangement. Geometry, octahedral. Shape of XeF4, square planar. Okay, hybridization sp3d2. Next compound of xenon, that is xenon fluoride, XeF6 xenon hexafluoride. Xenon hexafluoride. Let's calculate the steric number to predict the hybridization of xenon in XeF6. What is the hybridization of xenon in XeF, students? Can you answer? Now you have that knowledge to calculate the steric number. First to calculate the steric number. How many electrons are available in the valence shell? 8 plus 6 into 7. So 42 plus 8, it is 50 divided by 8. So what is that? 6 bond pairs, Q plus R by 2. Lone pair, so it is 2 by 2. Is that clear? So this is 6 is the number of bond pairs. Number of bond pairs. This is number of lone pairs. All total 7. When steric number is 7, what is the hybridization, students? Yes, it is sp3d3. And what is the geometry of sp3d3 hybridization? Geometry is pentagonal bipyramidal. I repeat, for sp3d3 hybridization, what the geometry? Pentagonal bipyramidal. But the regular geometry is not possible for XeF6 also. Why? It has got lone pair. When the lone pairs are present, molecule shape of the molecule distorted. One lone pair is present, we can't say it is pentagonal bipyramidal like XeF2, XeF6. In XeF2 hybridization sp3d, we are not saying sp3d hybridization means it is trigonal bipyramidal. XeF2 shape is linear. XeF4 shape is square planar, though it has got 2 lone pairs. Similarly, XeF6, it has got 1 lone pair. Its shape cannot be pentagonal bipyramidal. Though hybridization suggests it should be pentagonal bipyramidal, no. Due to presence of the lone pair, shape is distorted octahedral. I repeat, distorted octahedral. Distorted octahedral XeF6. Okay. Nowadays it is also called capped octahedron. Capped octahedron. So you better say distorted octahedral XeF6. Let me show you the structure of XeF6 on the whiteboard. Okay. Xenon, fluorine. There are 4 fluorine here, 2 more fluorine here. This is fluorine and this is the lone pair here. It is called distorted octahedral or capped octahedron. All the shapes are also displayed on a TV screen. Let's have a look there also. So XeF2 linear, XeF4 square planar and XeF6 distorted octahedral or cap octahedron. Next, the structure of or the shape of xenon oxides and xenon oxyfluorides. So XeO3, which is produced by hydrolysis of xenon tetrafluoride and xenon hexafluoride. It is xenon trioxide. Once again, let's see what the hybridization of xenon. Students, be quick, tell me what the hybridization of xenon here. Yes, calculate the steric number. Very simple. What the steric number here? So that is xenon 8 electrons, steric number calculation. Xenon 8 electron, oxygen 6 electron, 18 plus 8 26 divided by 8. So it is 3 plus 2 by 2. How many bond pairs? 3 bond pairs. How many lone pairs? 1 lone pair. 3 bond pairs, 1 lone pair. Then what is the hybridization? What is the shape of the molecule? Hybridization is sp3, no doubt, because 3 plus 1, 4. What is here? 3 plus 1, it is 4. So hybridization sp3. The arrangement of the orbital in space, tetrahedral. But what is the shape of the XCO3 molecule? 1 lone pair is present. We can't have regular geometry. Hybridization sp3 does not mean that it would be tetrahedral. Because of the lone pair, the shape is pyramidal. It is trigonal pyramidal XCO3, the explosive compound produced by hydrolysis of XCF4 and XCF6. Okay, students? So it is pyramidal due to presence of the lone pair like ammonia. So these are the shapes of xenon compounds we have discussed here. XCF2 linear, hybridization sp3d. XCF4 hybridization sp3d2 should be octahedral but square planar due to presence of the lone pairs. XCF6 hybridization sp3d3 should be pentagonal bipyramidal but it is distorted octahedral. XCO3 hybridization sp3, it should be tetrahedral but it is trigonal pyramidal. Okay, students? Well, we have discussed about the shapes of xenon fluorides and xenon oxides like XCO3 xenon trioxide. Let's see two more compounds, their shapes, xenon oxyfluoride compounds, XCOF2 and XCO2F2. Let's see that what is the shape of xenon oxyfluorides. It is XCO2F2. So what is the shape of the XCO2? In order to predict the shape of the xenon oxyfluoride, this compound, we have to calculate the hybridization of central atom. We have to predict the hybridization of central atom. For this, we have to calculate steric number. You know the formula to calculate the steric number. Can you tell me what the steric number here? Student, steric number of xenon. So steric number here, xenon has 8 electrons, oxygen 6 electrons, fluorine 7 electrons. All total how many electrons are available in the valence shell? It is 12 plus 8, 20 plus 14, 34 divided by 8. 34 by 8, it is 4 plus 2 by 2. So this is lone pair, this is bond pair, all total 5. Hybridization is sp3d. When hybridization is sp3d, what is the geometry of the this molecule or of the hybridization? If it is sp3d, geometry is trigonal bipyramidal. Hence, XCO2F2 should be trigonal bipyramidal, but there is a lone pair. When there is a lone pair, shape is distorted. So what the shape of XCO2? Let's see. Let's see where to place the lone pair. I've already told you in trigonal bipyramidal geometry, lone pair should be placed in equatorial position to avoid the repulsion. So lone pair must be here at the equatorial position. And I've also told you that electronegative atoms should be placed axially. And oxygen, as you know, oxygen forms 2 bonds, could be double bond with the central atom. Let's see what the shape of the XCO2F2. Hybridization of xenon is sp3d, but there is a lone pair. This is the shape of the XCO2F2. Can you tell me what is the shape of the XCO2, this molecule XCO2F2 shape? Can you tell me what is the shape of this molecule? It is seesaw. Seesaw shape. Okay? The XCO2F2, the shape of the XCO2F2 is seesaw. Hybridization of xenon, sp3d. How many lone pair? 1 lone pair. How many bond pair? 4 sigma bond pairs, and oxygen, since it forms that is a double bond, I mean 2 bonds, there is a double bond here. So both the bonds, what type of pi bonds are there? This is one pi bond here, here also one pi bond. What the nature of the pi bond? How the pi bonds are formed? By sidewise overlapping of or p orbitals or d orbitals. So here both the pi bonds are p pi d pi bonds. Why p pi d pi bonds? Because xenon hybridization is sp3d, already p orbital involved in hybridization. No more p orbital of xenon is available for sidewise overlapping. Then what is the hybridization here? What is how the pi bond is formed here? The pi bond is formed due to sidewise overlapping of d orbital of xenon and with p orbital of oxygen. So d pi p pi bond, both the pi bonds are d pi p pi bonds. What do you mean by d pi p pi bonds? Because there is sidewise overlapping of d orbital of xenon with p orbital of oxygen. Sidewise overlapping of d orbital of xenon and p orbital of oxygen results pi bond. So this pi bond is called d pi p pi bond. Why d orbital of xenon? Oxygen does not have d orbital. Why then xenon? Because hybridization of xenon is sp3d. So if it is sp3d, no more p orbital available. So obviously d orbital vacant or d orbital has unpaired electrons. So the d orbital is available for sidewise overlapping. Next compound, the structure of the next compound, HCOF2. Once again calculate the steric number. Students, yes, tell me, be quick. How many electrons here? Total valence electron 8 plus 6 plus 2 into 7. So 14 plus 14, 28 divided by 8. It is 3 plus remainder, it is 4 by 2. So this is lone pair. 3 bond pairs, 2 lone pair. 3 bond pairs, 2 lone pair. Total 5. Hybridization, if steric number is 5, hybridization is? Yes. Hybridization is? Yes. It is sp3d. So shape is, geometry is trigonal bipyramidal. sp3d hybridization, geometry is trigonal bipyramidal. Once again, how many lone pairs? 2 lone pair. I have told you where to place the lone pair. Equatorial position. Equatorial position. And where to place the fluorine atom? Axial position, electronegative atom. Where to place the oxygen atom? Oxygen atom should be placed equatorial position, that is less electronegative. Let me show you the shape of this one. Two lone pairs here. Okay. Or you can write like that. It will be better. Okay, 2 lone pairs, equatorial position, 2 lone pairs, and see the HCOF2, this is the shape of the HCOF2. It's better to have this type of shape, HC double bond O, F, F, this one, just invert that. This is the shape of the HCOF2. So what is the shape of this molecule? Remember, if hybridization is sp3d, 3 bond pairs are present, 3 sigma bond pairs, and 2 lone pairs, the shape is T shape. T shape. See, this is T shape. T shape. So these are the structures of the xenon compounds, the shapes of the xenon compounds. Okay, so better to follow this one. That is better to look at. I am erasing this one. Then coming to uses of inert gases. Uses of inert gases: helium is non-inflammable and light gas, so it is used in filling balloons for meteorological observation because it is lighter, very light gas. Helium is used in gas cooled nuclear reactor. Helium oxygen mixture is used 80% helium, 20% oxygen. This mixture is used by sea divers, okay, for respiration. Not the air, that helium or nitrogen mixture, that can't be used because nitrogen dissolves in blood under high pressure inside the sea, and when the sea diver comes to the surface, that causes painful disease called bends. Liquid helium is used as cryogenic agent. Helium is used to produce powerful superconducting magnets also. Argon is used in inert atmosphere in metallurgical process. Xenon and krypton, they are used in light bulbs designed for special purposes. Okay, these are the uses of helium. Mostly helium is used for that is used in filling up balloons for meteorological observation, and helium oxygen mixture is used for this mixture 80% helium, 20% oxygen. This mixture is used by sea divers for respiration. That's all for the noble gases, students. So, we have discussed the physical properties, chemical properties, compounds of xenon, that fluorides of xenon, oxides of xenon, and the uses of noble gases or inert gases. So, with this I come to end of this topic. So, thanks for watching this video. Thank you very much.